Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will start our study of multiple linear regression. We will be discussing an example that will show us that many of the things that we already know about simple linear regression can be useful or easily extended to the multiple linear regression case. Okay, so let's begin. Let's talk about that example. So take a quick look at this slide. Okay. So basically what we have there is the description of one of the predictors we will be using in this case. Okay. Now let me show you the next slide. The next slide contains not only this predictor, okay, it contains another predictor and the response variable that we are interested in, okay? And as you can imagine from the information contained in this slide, the response variable, the variable that we would like to be able to predict, is the plant's electricity usage. Okay, and this is one of the variables that we're going to be using to try and predict that variable. Okay, so let me show you the next slide, the one that contains the full data set. Okay, so these numbers here, first column is the one, the first column is the one that we are going to be using as our response variable. Okay, and CDD is going to be one of the predictors, the other one is going to be production. Okay, so now what I would like you to see first is that in this case, for this model that we're going to be constructing, instead of having a single predictor, we are going to be having more than one. We have two. Okay, but you'll see that the ideas that we have already discussed in the case where you have a single predictor, just one, will be very useful or are going to be easily extended for this case where we have more predictors. Okay, so next let me show you the model that we're going to be considering. Remember that before, right, when we talked about simple linear regression, sometimes we would talk about two different models, the centered model, right, and the classical simple linear regression model. Okay, so in this case we have an extension of the classical simple linear regression model. We're not doing anything to the predictor variables. Okay, so in this case, as we could see from that table that contains the full data set, we have two predictor variables, right? Production and CDD, cooling degree days, right? Same as before, we believe that the relationship between those predictors and the response variable is roughly linear, and that we have these random fluctuations, these epsilons. The assumptions, the assumption about the the epsilon, the assumptions, because there's more than one, right? Okay, so the assumptions about the fluctuations, the epsilons, are going to be the same. We are assuming that they are normally distributed, mean 0, variance sigma square, meaning we have a constant variance, right? We are assuming that they are independent as well, okay? So the assumptions remain the same for this multiple linear regression model. But now, instead of having just two parameters like we had before, beta 0 and beta 1, now we have three parameters for this part that defines the average for the response variable, right, the expected value, right, and we have a fourth parameter, sigma square, right? Okay. Now let's try and express our data set, right, using this model, right? So we can rewrite our linear model using matrices, and we at some point, right, remember that we did something similar for the simple linear regression model. So this is not so new, right? We have done something very similar to this before. Remember that we have data for a year, right? So we have 12 observations here, and the model that we had here, right? Remember that this would be the same as just 1 times beta 0 xi 1, meaning, and we have the ith here because it's the ith observation, and it would be the ith value. Well, it would be the it would be the ith value of that column, right? And we have the second subscript because that's for the first predictor variable, right? And then we have something similar for the second predictor variable. Anyway, so what I wanted you to see is that we could express this using matrices. This would be a 1, this would be the value for the ith observation for the first predictor variable, and this would be the value for the ith observation for the second predictor variable, right? So we have something like this, and if you multiply that matrix, which would be in our particular case a 12 by 3 matrix, that would be the dimension of that matrix X, right? Then it would be a 12 by 3 times a vector that contains 3 parameters, beta 0, beta 1, and beta 2. 3 by 1, those are the dimensions of that vector, right? And this guy here, we're using epsilon without a subscript to denote the vector of random fluctuations, which we don't get to see. That's an unobserved vector, right? But anyway, that's what the model looks like. So we would have 12 epsilons here. Okay. Okay. So next, a little bit of let me mention something about terminology. We are going to be referring to the matrix X as the design matrix. Okay, and as I pointed out earlier, in our particular case, this guy, the design matrix X, it's going to be a 12 by 3 matrix. Okay? Okay. Now let's just recall a little bit of the things that we have learned, right? and how we are going to be extending those ideas from the simple linear regression model to derive solutions, answers for this kind of problem. So we have, thanks to our matrix algebra, thanks to our matrix representation, we were able to rewrite the regression model like this, right? Y, this uppercase Y, represents a vector, right? Not just a single observation, but a vector. In our example, the dimensions of uppercase Y, this guy Y is going to be a 12 by 1 vector. Okay, so those are the dimensions of the matrix Y, or vector in this case, if you will. So the dimensions of X, 12 by 3, dimensions of beta, 3 by 1. This guy, the random fluctuations, a vector, an error vector, 12 by 1. Okay, this guy here represents, as we said here, right? It's a systematic component, right? So it's the part that we are assuming we're going to be able to model mathematically with a linear function. Okay, and this is something that it's just random. There's a random fluctuation there. We have a probabilistic model for those guys, right? And then the idea is, as you recall, right, we would like our predictions, which would be given by x beta hat, so it's a particular value of the beta vector here. We want that beta hat such that the difference between what we saw, y and x beta, that difference is as small as possible, right? That's what we would like to do, minimize that difference. Okay, so if you think about it, right, in this particular case, we have this kind of a situation. So our first observation looks like this, right? Let me write it down like this. Beta 0, beta 1, x 1, 1, plus we have a beta 2, x 1, 2, right? So x 1, 2. And we have that particular epsilon term for the first observation. Okay. Then we have something similar for the second one. Let me copy paste this guy. So this guy is the second observation. Second observation. Second observation. Have another one for this guy. The third one. And again, note that now we need a double subscript because, we have more than one predictor variable. Let me write down the last one, the nth one. Okay. So, but the idea is that we would like to find, to estimate beta, right? That's what we would like to do, right? We would like to estimate this guy. So what we said is the idea that we had before can be extended, right? What we said is before, when we were talking about just having a single predictor, right? What we wanted to do is finding particular values of beta 0 and beta 1 back then, right? Such that the difference between what we observed and what we predicted was small, right? So can you see that just like before, you know, those differences are given by those random fluctuations that we don't get to see. So what we would like to do is make that difference. We propose some particular values and make those differences as small as possible. Remember when we talked about simple linear regression that we said that for mathematical reasons it was so much easier to minimize the square of those differences? Remember that? So instead of this guy directly, what we minimize is the square, right? And we don't do it just for one observation like we did here for the last one, right? That would be only the error, the squared error for the last observation. We do that for every single one of them and we add them all up, right? So that was the idea. So we did that for every single observation in our data set. Okay? I think that when we talked about this, we called this guy a function q. So we wanted to minimize q with respect to beta 0 and beta 1 back then when we talked about simple linear regression. Well, now we want to minimize that same function with respect to beta 0, beta 1, and beta 2, right? So what would be the next thing that you would naturally do if you wanted to minimize that quantity? Well, you would just take partial derivatives, right? Differentiate with respect to beta 0, beta 1, and beta 2, right? So back then, when you did that with respect to beta 0 and beta 1, you ended up with a system of equations, right? And those, well, we called that system of linear equations that resulted after you took the partial derivatives with respect to beta 0 and beta 1, right? We gave it a special name, the normal equations. Remember? Well, we are going to have the same thing here. Okay? Now, the only thing is that instead of having a system of linear equations with only two equations, because back then when we discussed simple linear regression we had only two parameters, beta 0 and beta 1 here. Now we have three. Well, it's going to be a 3 by 3 system of linear equations, but that's something that we can solve, right? No problem. Okay, so let's go back to our lecture notes so I can show you what we have here. See, that's the Q function, right? Can you see that this guy here, right? Q is just the summation of those squared errors, right? These guys here inside the square brackets, those are the epsilons, right? So that's what we have there in our lecture notes. Another thing that we're doing here in our lecture notes is just underlining that you could express the epsilon vector, right? Those differences that we have here, you could rewrite that using a matrix notation, matrix representation. This would be the vector y, right? And what you have here is the same as x times, where x is the design matrix and beta is the vector of parameters, right? You will have this here. But just, using matrix notation, and remember that we are using just epsilon without a subscript to denote that vector that contains all the epsilons, all the random fluctuations, right? Okay. So this is just using matrix notation. But as you can see, this is going to be a quantity. Using jargon from linear algebra, that's going to be a scalar, right? This. Okay. As we were saying just a couple of minutes ago, next step, well, take derivatives with respect to beta 0, beta 1, beta 2 in this case, and set them equal to 0. You will end up with a system of equations. That's what we call the system. Well, we call that system the normal equations. You solve, and that's it, right? Something else that we said, and we talked about this when we talked about theorem, where you could think about this problem of linear regression as solving a system of equations. You have seen the expression that I'm about to show you before. If x transpose x, right, it's invertible, right? If the inverse of x transpose x exists, then, well, just you pre-multiply by the inverse of x transpose x, and you have beta hat, right? You have seen that expression before. Okay? So the only difference from what you did before and what we're doing now is the dimension of the design matrix, right? Before, instead of having 3 columns, you had 2, right? But very similar. Okay. So now remember that when we talked about residual analyses, we realized that the H matrix, the hat matrix, is very important in linear regression, right? Okay, so again, let me remind you where that matrix comes into play, right? So here we have that if we pre-multiply beta hat, the least squares estimate of beta, by x, the design matrix, you will end up with our predicted values, what we call y hat, right? Those are our predictions. But if you do that, then you have this expression here, x beta hat equals x times x transpose x inverse x transpose y, right? Okay, so if we think about this, the kind of ugly looking expression that pre-multiplies the response vector y, if we think about this as a single matrix, as the matrix H, right? That expression defines the matrix H, and then we realize that if you pre-multiply the response vector y by H, then you're going to end up with the predicted values. Okay? Okay. Again, in residual analysis, we also saw that we can use a matrix that is related to the hat matrix to obtain the residuals by using a matrix multiplication. So since the residuals, right, and it's something like what we have here, right, the vector of residuals is obtained like this, the difference between y minus x beta, right? So once we have our predictor, once we have our estimate of beta, then we have our predicted value for y hat, and then the difference y minus y hat is going to be an estimator of epsilon, right? That's why we have the hat here, okay? But we could rewrite this, the difference between y minus x beta hat, as y minus h times y, right? And then if you just factor out that y vector, you end up with the identity minus h, right? That's what we have here. That I represents an identity matrix. In this case, it would be an identity matrix of dimensions 12 by 12. So we would have on the diagonal 12 ones and zeros elsewhere. Okay? Okay, so something else. Remember that we have a fourth parameter to estimate here. We have beta 0, beta 1, beta 2. Those are the three betas that we want to estimate, but we have another parameter, sigma squared, right? The variance of those random fluctuations. And so we know that it would be nice to have the sum of squares of the error, right? So we know that this is going to be useful, right? If, I mean, this is basically this, right? So if you want to express that sum, right, using matrix notation, well, that's the same as epsilon hat transpose times epsilon hat, right? But using that expression that we have for epsilon hat, I minus h times y, we have this, so it would be the transpose of that. Now, remember that at some point, again, when we talked about residual analysis, we said that the matrix H and that the matrix I minus H satisfy two interesting properties. They are symmetric, meaning, in the case of I minus H, well, I minus H transpose equals I minus H, okay? And the other one, the second property, is that I minus H and H too, both of them are idempotent, meaning that in the case of H, H times H is going to be equal to H, and in the case of I minus H, well, it's something similar. I minus H times I minus H gives you I minus H. So both of them, H and I minus H, are symmetric and idempotent. So this is one way of expressing the sum of squares for the residuals. using a matrix multiplication that involves the matrix I minus h. Okay? Okay. So, and remember that we talked about how we can estimate the variance sigma square. In the case of simple linear regression, we had SSE divided by n minus 2. Now we know that one way of rewriting SSE using matrix notation is, the product, the inner product between E hat and E hat, right? So that's E hat transpose times E hat, right? It's just another way of, expressing the sum of squares for the error, okay? Now, note that instead of dividing by n minus 2 like we did before, we are dividing by n minus 3. So you also remember that we showed that in the case of simple linear regression, we wanted to divide by n minus 2 because we wanted this estimator to be unbiased, right? Meaning that the expected value of this quantity was going to be sigma squared, okay? So in this case, instead of having two betas, beta 0 and beta 1, like we did before in the case of simple linear regression, now we have 3 betas. So that's why we're going to be, using n minus 3. If we had, say, 4 betas instead of 3, as you can imagine, we will be subtracting a 4 here. Okay? So, in general, and I think this is the notation that Walkerly uses in his textbook, he uses k, the number k, to refer to the number of predictors. Okay? And we have that plus 1 because we have the intercept. So, like in this case, we have two predictors. We have electricity usage, and we have, we have two predictors. We have production, and we have cooling degree days, CDD. So we have production and CDD, okay? So K would be 2, plus, that one for the intercept, then you have 3 total, okay? So I'm just introducing this notation with the K, so you feel familiar with that. But the thing is, what you're going to be doing here is dividing by n minus the number of betas in your model. Okay? And that includes beta 0 as well. Okay? Okay. So, now, what if we try and do this? See if our our matrix expressions, our theoretical expressions work for our example. So let's launch R. First step, as usual, we have to enter the data. So we know that the first column is our response variable, right? Electricity usage. It's the one that we want to predict. Here we go. Let me use Y for that guy. Done with Y. Let me check that I have 12 observations. Okay. Let me check 2.48, 2.26, 2.47, 2.77, 2.99, 3.05, 3.18, 3.46, 3.03, 3.26, 2.67, 2.53. Okay. Seems to be okay. Now, let me use x1 for the first of our predictors for production, right? Okay. So we have 4.51, 3.58, 4.31, 5.06, 5.64, 4.99, 5.29, 5.83, 4.70, 5.61, 4.90, 4.20. Let me check that we have 12 observations here. Yeah, so seems to be okay. Let me quickly check. Okay, I think I recorded those guys correctly. Let's do the same thing. Let's record. Let's enter the values of the second predictor variable. Okay. So again, the purpose here in this video is seeing if our matrix expressions, if our theory is going to help us get the same results that we would get using built-in functions that R uses. Okay? Okay, so first, since we want to check our matrix formulas work, let me turn our data into matrices, right? So just to make sure, since we are going to be doing matrix multiplications, and in some cases we're going to be trying and finding inverses and so on, let's make sure that R knows that Y, that vector, is a vector, right? Or a matrix with, in this case, 12 rows and 1 column. Okay. So looks fine. Let me see. Okay. It is what we want, yeah. Double checking. Okay, now let's create the design matrix using R. Let me call that first column of our design matrix 1. And what I'm going to be doing is I'm going to be repeating the value 1 12 times because, you know, we need 12 rows. Okay. So that's what 1 looks like, but I want that guy to be a matrix at some point, so when we paste together the columns of our design matrix, we're going to do something similar to what we did with Y. We're going to make sure that R knows that X, the design matrix, is in fact a matrix. It has that format, so R can, you know, carry out the operations that we need. So let me use the function cbind to paste the vector I just created, 1 and x1 and x2, our predictors. Okay, so if you take a look at x, it seems to have the right form, right? 12 rows, 1 column, 12 rows, 3 columns, and the values seem to match with those that we have in our table. So, okay. So again, matrix X has 12 rows, 3 columns, and we want to make sure that X uses X as a matrix, right? So number of rows, 12, number of columns, 3. Okay. There. Great. Now, let's go back to our beautiful expression for beta. Let's see if it works. We know that we have to do something like this. We have to use that expression, x transpose x inverse x transpose y, right, if we're going to be finding it using matrix multiplication. So let me call this beta. Oh, well, first, let me just say something. So we have the transpose of x, right, times x, right? That's the first thing that we would need. I mean, that product, x transpose x, then inverse. I just want to make a comparison between what we had before and what we're having now, okay? It's going to be quick, thanks to R, okay? So see, before, right? I don't know if you remember this, but before, when we did that, we ended up with a 2 by 2 matrix, right? So the difference now is just the dimension of the matrix, right? And then again, so we will need to find the inverse of that matrix. So we can solve, and then we have a 3 by 3 matrix, and using that solve function, we get the inverse of the matrix x transpose x, right? And then finally we need to multiply by transpose, well, with the transpose of x times y. So let's do that, no problem. Now, as you can see, we end up with a vector, a 3 by 1 vector, as we should. This would be beta 0, this would be beta 1, this would be beta 2. Okay, so now let me call this guy our beta hat. How's that? Okay. Okay. Now, we were saying that we could use the H matrix to obtain, right, the predicted values, right? So let's check that the theory works. So let's define that matrix H, and maybe something that we have here will be useful. Yeah. So let me borrow some of this, right? So we know that the H matrix, right, it's here. It's this guy, x times x transpose x inverse x transpose, this chunk here. So let me recycle what we had to obtain beta hat. So the only thing that I need to have H is pre-multiply by x, right? The sign matrix, and then I'll have my matrix H, right? Okay. What did I do wrong here? Oh, right. That's better. Okay. Nice. So let me save that in an object that I'm going to be calling H naturally. Just let me show you something. If we did everything well, we know that this should be a 12 by 12 matrix. So yeah, the dimensions of H check out. Good, good, good. Now let me get H hat, using H. Let me pre-multiply our vector of observations y by H. So this should give us a 12 by 1 vector, and those, if the theory is not lying, those should be our predicted values. Okay? Okay. Something else. How about we get our residuals using this approach? So let me create a variable n that gives you the length of the vector of observations. Now let me try and find the residuals using our H matrix. We know that it's going to be I minus H. That's the matrix that is going to help us find the residuals. So I want a diagonal matrix. N is going to be 12 here because that's the length of my observed vector, right? And then I already created that matrix H, and then all I have to do is multiply the observed vector y, right? This would be I minus H. Okay, so let's see, 12 by 1 vector. Good, good, good. So we got our residuals using that. Now, remember that this is just for fun, just to check something. Remember that when we talked about residual analysis, right, and when we talked about inferential observations, we said that the sum of the diagonal elements, and the diagonal elements are the leverages, right? The diagonal elements of the H matrix is what we call the leverages. What we said is that the sum of the leverages equals the number of betas that you have in your model. So before, when we were talking about simple linear regression, the sum of the leverages was 2. Okay, so if again, the theory checks out, if it makes sense. In this case, the sum of the leverages should be 3, right? So let me call that guy just P, as in the number of parameters for the beta vector, okay? So sum of the diagonal elements of H, okay? Let's see. P is 3, so the theory is not lying. Okay, great. Now, what else? We said that we could use the I minus H matrix to get an estimator of sigma squared, the variance, right? Okay, so let me see. Yeah, so let's, and it's here, right? It's just this, right? Y transpose times I minus H times Y divided by, in this case, will be N minus 3, right? Okay. So let's just write that down, that multiplication, and again, then we're going to compare with the built-in functions that R has. So we have I minus H there in the middle, and we have Y here, yeah, okay. And then we want to divide by N, the number of observations, minus the number of betas in our model, and in this case that's contained in that variable that I called P. Okay, so let's see. Okay, it's there. It's a number because it's the estimator of sigma squared, the variance. So let me call it sigma 2 hat. Okay, it's the estimator of the variance of the errors. Okay, so that's the linear algebra approach, if you will, our formulas. Now let's do it in another way, a faster way. So we know that if we want to do a linear regression, a simple linear regression, the syntax was y, then a tilde, right? And then the predictor variable. Now we have more than one. So the syntax is, I have two predictors, so y tilde first predictor plus second predictor. Note that we're not creating, there's no need to when you use these built-in functions like LM, there's no need to create that vector of ones. Okay, it's already there. Okay, now first comparison. We know that if we want the coefficients of a linear model that was created using LM, you have that built-in function coef, and there you go. Now ours was called beta hat, right? Let me see, it was here. Our beta hat. Okay, so our beta hat, see, same thing. Okay, so now let's make a comparison between the predicted values using our approach and the one that you would, well, the ones that you would get using, you know, a built-in function. Okay, let's see, we call them just y hat. Yeah, okay. So let me use that cbind function so we can make a side-by-side comparison, right? And just let me remind you something first, that if you want to see what you have inside that linear model object you created, so in this case I want those fitted values. I want to compare the predictions between this built-in function and using the matrix approach. So here we go. Now let me use that cbind function, and then mod $fit. That's enough. Okay, that's going to give you the fitted values. Okay, and then ours is just y hat. Okay, see? So, and we created that y hat using just a plain matrix multiplication, the matrix H times y. Okay, that was it. Now, let's do the same. Let's compare the residuals. We know that the residuals are here, right? So if we type just res, I'm sure that R will give us what we want. And then our residuals, which we obtained by just using, again, a matrix multiplication that looked like this. I minus h times y, that's it, right? And let me see again the name. It's our res. So our residuals, see? Nice, right? So now we can see why that H matrix is so important, right? It allows you to get predictions just, using a matrix multiplication. It allows you to get not only predictions but also residuals, right? And it is something really nice. And also we know that H, right, has to do with leverages. It will allow us to find potentially influential observations. And we just saw that property, that the sum of the leverages equals the number of betas in your model, still holds, and it will hold in general. Okay, so now just since the residuals are the same, our estimator for the variance is going to be the same as the one that you would get using R. Okay? Yeah, we have our sigma 2 hat, right? Okay. For instance, one way of getting that sigma for our model would be this, but this would be just sigma. Remember that the one that you have here is sigma squared, right? So if you square it, you end up with the same thing, right? Okay. So let's summarize what we've done here together. So what we did is, using an example, right, we made a comparison between the things that we did before when we talked about simple linear regression, and see if we could still use some of those ideas, some of those formulas in the multiple linear regression setting. And what we saw is that in some cases formulas are not going to change at all, right? Like the expression for your beta hat, that's the same, right? In other cases, some changes have to be made accordingly. Like in this case, for the estimator of sigma square, the variance of your residuals, before, when we talked about simple linear regression, you divided by n minus 2. Now you have to divide by n minus 3. And if we had more than 3 betas, right, it would be, say that we had p betas there, it would be n minus p, right? Okay, so all those ideas that we have discussed thus far seem to be very useful and easily extended for the multiple linear regression setting. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.